To calculate acceleration due to gravity at all other locations besides the surface of the Earth, we're going to use the identity that the gravitational force is the same thing as weight. So we know this because the synonyms for gravitational force is the force of gravity, gravitational attraction, the gravitational force, or weight, all the same thing. Gravitational force, as we've been discussing, is big G, m1 times m2 over d squared. And weight we've been calculating by finding just mass times acceleration due to gravity. Acceleration due to gravity is, we use the symbol either a with a little g or mostly just little g. Make sure you distinguish very clearly the difference between acceleration due to gravity and force of gravity, because if you mix those up, you can't solve the problem right. So there's acceleration due to gravity, gravitational acceleration, that's one thing. That's this. Force of gravity is the same as weight, is the same as gravitational attraction. So make sure you know that. So before we can continue, we kind of have to identify what these m1s, m2s are. So m1, we generally say, is the mass of the system, the thing that, the smaller thing generally that's being attracted to the larger object. Another way to say that is to say that m1 is the orbiting object, when you have an orbiting object, and m2 is the thing being orbited. Okay? So if that's the case, then if you want to find acceleration due to gravity, what's this m? Well, this is the mass of the system. Well, we just said that m1 is the mass of the system. Therefore, we could write this m1 times g. And once you've done that, you can see that these will cancel out, or you can divide through by m1 and get rid of those. So we're left with big G times the mass of the object being orbited, or the larger mass object, generally the planet or the moon that you're on. And then you have the distance between the centers of the objects, and that will give you acceleration due to gravity. So this is the relationship that we'll use to find G. Now on the surface of the Earth, we know that little g is 9.8, but we could use the mass of the Earth and the radius of the Earth to calculate it, and we'd get the same thing. So in the two problems on the guided practice, we've got these constants, and it becomes a pretty simple thing then to actually calculate the value. On the surface of the moon, you're going to use the mass of the moon and the radius of the moon. Okay, so when you do that, you get 1.62 meters per second squared. All right, so then for the second problem, we have a satellite that's orbiting at an altitude of 5.73 times 10 to the 5th meters above the surface of the Earth, which sounds really far, right? That's like 57 kilometers above the surface of the Earth. What's going to happen to acceleration due to gravity? So we're going to use acceleration due to gravity, and we'll have 6.67 times 10 to the negative 11. We use the mass of the Earth because that's the object that's being orbited or doing the attracting in this case. And the altitude is going to be the radius of the Earth plus the altitude above the surface of the Earth. And then you square both of those. And that will give you a value of 8.24 meters per second squared. It's very important that you add those two things up. You can't, if you add you need from the center of the Earth to the satellite. The question you might have is, why don't I need to use the radius of the satellite? It's so negligible that it makes no difference. How big could the radius of a satellite be? Could it be 1 kilometer? So does 1 kilometer or 1,000 meters make any significant difference in this distance here? No, not really, and therefore you can ignore it. The same as we did in the previous problem when we were calculating the distance from the sun to the Earth. The radii really didn't matter. It's such a big distance. Why don't we use the mass of the satellite itself? Because we canceled it out. So you don't need it. All you need is the mass of what's being orbited.